Hello and welcome to my talk. I am Augusto Fasano and I'm about to present a scalable and accurate variational-based procedure for high-dimensional binary regression models, which is a joint work with Daniele Durante and Giacomo Zanella from Bocconi University. First, let me start with the motivation and the specification of the model. We are in a binary regression framework where, generally speaking, we study how the probability of success of some binary response y changes with a set of p observed predictors encoded in a vector x. So our data are composed by n binary observations, y1 up to yn, and the corresponding covariate vectors x1 up to xn. In particular, we model the effect of the covariates on the output via a Probit model, which in its classical Bayesian formulation states that our response variables yi's conditionally on some latent state vector beta are independent Bernoulli random variables with mean parameter given by a Probit map, that is a standard Gaussian CDF, computed in a linear transformation of the state defined as the scalar product of the corresponding covariate vector and the state vector beta. This model is then completed by taking prior distribution for beta, which is generally chosen to be a multivariate Gaussian centered in 0 with independent components. Such a model admits also a quite useful dual interpretation in terms of Gaussian latent variables, and in such an interpretation we have that our responses yi's are interpreted as indicators of whether such latent variables zi's are positive or not. And these latent variables are defined as the linear transformation of the state we have seen before, plus some Gaussian white noise. And since we are in a Bayesian framework, the main question is how can we perform posterior inference? Because a lot of research has been carried out in this Bayesian setting about this, mainly motivated by the fact that the posterior was apparently unavailable. And so different MCMC methods were proposed, most of them exploiting the latent variable interpretation we have seen before. But also approximate methods were developed, like mean field variational base or expectation propagation. However, these procedures are not well suited for large P settings, which is the main focus of this talk, because in such a framework they are either computationally impractical or they suffer from accuracy issues. And our first solution in this large P setting was actually given by Durante in a recent paper in 2019, who showed that the posterior distribution of beta is actually available in closed form, and it is a unified skew normal denoted sun Pn, where, for those of you who are not very familiar with this family of distributions, a sun Pn is parameterized by 5 parameters and has a density which is obtained by multiplying a p-variate Gaussian density and an n-variate Gaussian cumulative distribution function. And thanks to this result, we can exploit the sun additive representation to develop an IID sampler, because we can get a sample from a sun Pn by linearly combining a p-variate Gaussian sample and an n-variate truncated Gaussian sample. So we can easily see that such an IID sampler is well suited for high-dimensional scenarios, because we can sample from pretty large p-variate Gaussian vectors, but becomes rapidly infeasible as n gets large, because it's quite hard, even with recent techniques, to sample from large n-variate truncated Gaussians. And so this motivates our idea to develop a variational-based procedure which is accurate in large P settings, but does not suffer from the computational bottlenecks of the IID sampler we have just seen. And as maybe you already know, the general principle of variational base is to approximate the posterior distribution with the best possible choice in a class of so-called easy approximating densities. And in particular, here we focus on approximating the joint posterior distribution of beta and z, which can be shown to factorize as a product of two terms. A first term representing the distribution of beta given z that does not depend on the data, and this is an easy term because it's a p-variate normal density, which is multiplied by the posterior marginal distribution of z given y, which is the difficult part of this posterior distribution. And it is because it is an n-variate truncated normal density function. And so this motivates our idea to use a variational approximation for this joint posterior distribution and find this variational approximation such that it factorizes the multivariate truncated normal component via a product of independent terms. So, in short, we look for an approximating Q of beta and z having the following form. A term accounting for the dependence of beta on z, and this is crucially different from currently available mean field variational based solutions, which factorize the distribution of beta and z as a product of independent terms, one for beta and one for z, and then approximate the complicated multivariate truncated normal part with a product of independent components. And we want to find the Q having such a form, which is the best in terms of Kurbach-Leiber divergence from the true joint posterior distribution. And the first result is that the solution that we are searching for, so the Kurbach-Leiber minimizer in the class of distribution having this form, is obtained when we have that the term accounting for the dependence of beta given z is actually the true posterior conditional distribution of beta given z, which is the multivariate normal component we have seen before, and the individual terms describing the approximating distributions of the zi's are univariate truncated normal densities with variance component available in closed form and mean component that can be obtained through a coordinate ascent variational inference algorithm. And as a byproduct, posterior moments of beta are readily available, and also other important quantities can be computed either in closed form or via an efficient sampling procedure. Moreover, we call our solution partially factorized mean field approximation, which is denoted with the subscript PFM, in contrast to the mean field solution, which is denoted with the MF subscript. And a first fact is that our partially factorized mean field approximation always gives a better approximation with respect to the mean field solution. And moreover, under some non-restrictive assumptions, our partially factorized mean field solution is asymptotically exact, meaning that as the number of regressors diverges, the Kurbach-Leiber divergence between the approximating density of beta and the true posterior density of beta goes to 0 with probability 1. Moreover, as p diverges, our proposed method converges in one iteration. And these are peculiar properties of the partially factorized mean field solution because it can actually be shown that the mean field solution available in the literature is inaccurate in high dimensions. And it's not even able to capture the behavior of the first order moments, inducing a quite severe overshrinkage of these parameters, of these mean parameters, towards 0. And this different quality of approximation is also reflected in our empirical study on an Alzheimer dataset, where the response variables, yi's, represent the presence or absence of the Alzheimer's disease, and the covariates include demographic data, genotype, and assay results, and the pairwise interaction terms. So that we have 333 observations, of which we take 300 for training and 33 are held out to compute predictive probabilities. And the overall number of covariates is 9,036. And with this high number of covariates, we have that when we look at computational times of the available methods, STAN, which implements Hamiltonian Monte Carlo and expectation propagation after 6 hours, are not able to produce any output, while the IID sampler takes 1.5 hours approximately, being orders of magnitude higher than the computational time taken by the variational based approximations, which both the mean field and the partially factorized mean field both take 3 seconds to converge and compute the quantities of interest. However, this similarity in the computational time is not reflected in similar accuracy of the posterior approximation, because we can see from the plots where we have on the x-axis the first and second moments as well as the predictive probabilities computed with the IID sampler, and on the y-axis we have the same quantities computed with the 2 different approximations. We can see that our partially factorized mean field, which is represented by the dark gray triangles, perfectly matches the moments and the predictive probabilities, while the mean field solution induces a severe overshrinkage of the moments towards 0, and this implies a severe overshrinkage of the predictive probabilities towards 0.5. So, I hope you enjoyed the talk. In such a case, you can find the main reference on the archive, and if you are interested also in possible extensions to categorical data, here is another reference available on the archive. Thank you very much for your attention.